Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And we're in a little mini series called Split Plot Design. We're on part 4, and we're going to look at the column spaces of the design matrix. Now here we're going to look at the model, split plot model, randomized complete block. And I would encourage you to watch parts 1 and 2 for more in-depth of explanation of this. But essentially the first randomization occurs with the randomized complete block design. So if we were to cover up the model, this looks like a randomized complete block design. So we have the first factor effect and the block effect and the error term. And then the second randomization of the second factor is done within those whole plots. And we have the gamma and the alpha gamma interaction plus the, that should be an S, not a 2. So then in matrix form we call it mu1 plus x alpha alpha, x beta space, the x gamma, the interaction, and then this error term, those two are combined into one. So now let's look at the perpendicular projection matrices. Now from part 3, we know that J, M alpha, M beta, M gamma, M alpha gamma projects onto these respective column spaces. So now we want to find the, an X alpha star and a beta X beta star such that these column spaces are all orthogonal. And the original column space is equal to this column space where we found new columns. So such that these are all orthogonal. Now since the column space of ones is a subspace of the column space of X alpha, then we can take the difference of those perpendicular projection matrices. So M alpha minus J, it projects orthogonally onto the column space of ones with respect to X alpha. So what that means is it lives in this space, but it's orthogonal to the one vector. And that's what we call X alpha star, that column space. And similarly, we know the column space of ones is a subspace of the column space of X beta, right? Because if you were to add all these columns, you get a 1, so it's clearly a subset. That means if we look at the difference of those perpendicular projection matrices, and I actually have a nice video on several videos on perpendicular projection matrices if you want to go back and see those. We know that M beta minus J projects orthogonally to the one vector, but lives within this column space of X beta. So let's call that X beta star. Now, since these two perpendicular projection matrices, right, the product is 0, then we know those column spaces are orthogonal. So then we're finished. So then we've found these 3 column spaces such that they're all orthogonal. Now, for the second piece, so that's this column space here. Now we need to work on this column space. First of all, we need to make those orthogonal. Then we need to make these orthogonal to this space. So since X gamma, column space of X gamma, is a subspace of the column space of X alpha gamma, then we know the difference of those perpendicular projection matrices projects orthogonally onto the column space of X gamma, but with respect to the column space of X alpha gamma, right? Which is what we're going to call X alpha gamma star. So this column space is equal to this column space, but these two column spaces are orthogonal. So now you might ask, why do we need column spaces orthogonal? And that's so we can partition the total sums of squares. That's sort of our goal. And then we can develop F-tests and stuff like that. So for part 3, so what we've done so far, we've created column spaces for this that are all orthogonal. We've created column spaces for this where they're orthogonal. And then the next step is we're going to make these orthogonal to these. But it's a must watch. I have a video on balanced incomplete block design, and for great detail you have to watch that. So now we want to make these two column spaces orthogonal. We'll skip some details, but we'll follow this balanced incomplete block design video. So note that this column space is a subspace of the column space of that interaction space between alpha and beta, right? Now sometimes we call it XW if we're in the CRD design. So we know that M alpha beta projects onto this column space. So that means I minus M alpha beta projects orthogonally onto this column space. So if we pre-multiply this column space times this perpendicular projection matrix, we know that it projects orthogonally onto X alpha beta, which means it's orthogonal to these vectors. So we have this. So our original column space is equal to this column space. And again, I skipped some steps in that, and you need to go back and look at the balanced incomplete block design. But essentially we're adding a well-chosen zero to the model, and then we manipulate it and we can end up with this. But now, so now all these column spaces are orthogonal. But we need to get a little better handle on what this tells us right here. So the perpendicular projection matrix onto this column space right here is this. And it's essentially equivalent to putting the perpendicular projection matrix here and then multiplying it out. And then this times that is M gamma, and this times this. The only thing common is the 1 vector, so it projects onto the 1, which is equivalent to J, the perpendicular projection on the column space of 1s. Now, I skipped some steps to go from here to here, but this is true. Now, I would encourage you, and actually if there's any comments on wanting me to derive to go from here to here, let me know. But then the perpendicular projection matrix onto this column space is essentially put the perpendicular projection matrix for this here and then multiply it out. And you get this. When you that times is this times this is we do, yeah, this times this times this. Oh, this is M alpha, so it's minus. That's J. How do we, 1? Oh, this times that is that. I got it. And that times that is M alpha. This times this is J. Now 4, let's let M be the perpendicular projection matrix onto this. And now I have a video on titled The Sum of Perpendicular Projection Matrices. But essentially, if we have orthogonal columns, then we can add the perpendicular projection matrices of each column space, and then that equals the overall perpendicular projection matrix. So here we have J, right? We have M alpha minus J, this one, right? We just derived. That one is this one. Now, we're going to kind of group these together and bring them down, and then we'll group these. We'll add, the J's cancel, the alpha cancels, and we're left with this. Now we're going to generically call this M1 and M2, and these are orthogonal, but we could also just add them and come up with this. So this is M, but the reason we leave these separate is when we start dealing with contrast, we have to put constraints on each piece, the split plot design or the whole plot design. We have to be careful with that. So now the split plot model for a completely randomized design is this, right? And if you were to cover this up, that's a completely randomized design for the first factor in our design. This is for the second factor. And again, watch videos 1 and 2 for more detail. Now we break it up into matrix form, And then the goal is to create orthogonal column spaces for each of those. So we can let M be the perpendicular projection matrix onto this. And then we just add, so once we orthogonalize each of the column spaces, then we just add them. So it ends up being J, this, that, and that. And you do it similar to what we did up here. And then we keep them separate. So this is here, and this comes down. We'll call them M1 and M2. But if we were to do the math, it would just be the perpendicular projection matrix onto alpha gamma. Now, we're going to use M1 for contrast on the whole plot parameters, and we're going to use M2 for contrast on the split plot parameters, right? Because there's different errors associated with each of those column spaces. So we have to be very, very careful. Now, some quick derivations for part 7, and I didn't know where to put this. If I put it in part 7, it made the video too long. But if we take J times X gamma alpha times this vector of parameters. Now already we know, since J is the perpendicular projection matrix on the column space of 1s, our answer is going to be some constant vector, right? So now when you multiply this out, you get this. And then this is a column, a rectangular matrix of 1s, dimensions TR M rows and T times M columns. And then when you do this, and then divide by TM, you're getting the average of those for every row, which ends up being the constant vector. Now, so this is what we have here. So the number 2, J times this, again, we know it's going to be a constant vector. So this multiplication is this, and then when you do that, it ends up just being the mean of the alphas, times the 1 vector. Same way here, J x beta times the vector of betas. This, you get this, and then when you multiply that out, it just is the constant vector. Now this one is a little tougher here. So M alpha, X alpha gamma. I write what this is here. It's a block diagonal, and then this, and then that. Then when you multiply this times this block diagonal, you get this. You get another block diagonal, but the diagonal matrices are rectangular. And then when you multiply this out, you end up getting this vector. And now, one thing to note is we knew that it was going to be in the column space of X alpha. And there, it's remember the 1s. So this is like treatment 1, level 1 of factor, the first factor, level 2 of the second factor. And actually that's what those represent. And this one, remember, the ultimate answer is going to be in the column space of X beta. So this times this, well, we just get X beta back. And then this times this, we're going to get this vector, which then it's this repeated T times, which this is in the, this is in the column space of X beta. All right, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like it and subscribe so you don't miss the next one. Thanks. Bye.